Hello everybody and welcome to week 12 of Building Scalable Distributed Systems. Last week we looked at the technologies that you can use to move and acquire and very rapidly process information that's flying around the internet. Some information though requires much more deep analysis, and this requires you to use technologies that are designed to analyze this data at scale. So in this module, we'll just quickly look at the motivations for those technologies, for those platforms, and then give you a quick overview of Hadoop and Spark, which are two of the leading, most widely used technologies in this space. So when you do data analysis, the graph on the right shows the most widely used languages for doing data analysis. Python, very widely used, probably increasingly more widely used. R still dominant in many areas, SQL. But all of these are designed for relatively small data sets. You can do really effective experimentation and what-if analysis using these technologies. But typically, it only works well if everything, all the data you're analyzing, fits on a single machine. If you have a very large amount of data and you're trying to run a Python script or an R script on that, then it's basically going to do nasty things to the memory and the processor, because one machine just isn't enough to fit modern size data sets that need analysis. Some of these are in the terabyte to petabyte range. So as you can see on this little graphic here, the world is evolving over, probably in this example, maybe 30 years, where we now have immense data sources that are changing incredibly quickly. So every 60 seconds, this data's way out of date, but it just gives you an idea. You're getting like 100,000 tweets, 700,000 Google searches, nearly 2 terabytes of data created every single minute. This is an awful lot of data. So when you're processing data, you've got to read through a very large data set, let's say a terabyte. If we have a terabyte on a typical disk and we try to read through it at a typical read rate of 100 megabits a second, it's going to take us about 2.5 hours to read through that terabyte of data. That's not really very fast. And of course, writing is slower. So one way to improve the efficiency of accessing very large data sets and being able to do analysis on them is to read partitions of the data on different disks in parallel. So if we partition that 1 terabyte data set over 100 disks, we can read through the whole thing in 2 minutes. So this gives us a clue on how we can do scalable analytics. We need to divide the data up across multiple disks, which we can access and process data from in parallel. And this is where MapReduce and its current contemporary implementation, open source implementation, Hadoop, enter the scene. It's based on the Google Bigtable technologies that were invented by Google. And Hadoop has been open source for the best part of a decade now. It comes with a file system, the Hadoop file system, which is designed for storing very large data sets and reading through them very, very efficiently. It's not really designed for writing very efficiently. HDFS also will distribute data partitions by default 3 times across your cluster, so there's 3 copies of everything. And this means when you're doing a read of a copy, if the disk fails, then you can process another partition of that data just by finding it in the cluster. So it gives you a good degree of reliability in large data analysis. So how does a Hadoop work? It's basically built on an acyclic data flow model. And there's 2 phases in Hadoop that you program essentially. There's a mapper and a reducer. And if you look at the diagram here, basically what you see is that the data that this particular example job is processing is spread across multiple nodes, and the partitions, the data itself is partitioned on that node by default into 64 megabyte partitions. Then we have a mapping process on that node, and what the mapper does is it reads through the local data, effectively each partition, and if there's multiple mappers on that node, it will read through multiple partitions in parallel, and it produces some intermediate values. So let's say intermediate data from the mappers, and these are basically key value pairs. So every mapper will emit, based on its input partitions, a sequence of key value pairs. These key value pairs are persisted, so that if something fails, you can continue processing. But once they've all been produced by all the mappers, you can start earlier, but just effectively you wait till they all finish. All of the keys are aggregated and passed to the reducers, such that the same reducing process will see all of the keys that are emitted, all of the key value pairs that have the same key. Pardon me. So this means that the shuffle phase is basically shuffling the key value pairs, it's combining them together based on their keys and then pushing them to the nodes which are allocated to process those particular key values. Here's a very simple example, the Hadoop canonical word example. You can see the basic code that's required for a mapper and a reducer. So I won't go into the details here, and I'll let you pause the video and stare at it if you like, but as you can see, pretty straightforward. There's a map function, a map method. It takes some input values, and these are the input values that are being read from the input partitions in HDFS. And in this example, we just input a line, we tokenize it into words, and then for every word in that line, we do basically an output of the word as the key, output.collect, and the value 1, because each word is basically counted one time in that line. So these are all being emitted by potentially many mappers in parallel. And then once the mappers, all the keys are available, they will be combined. So all the key value pairs that were emitted by all the mappers for, say, example, the word frog, will be sent to the same reducer. And as you can see, a reducer just gets an input data set called values, and in this case it just iterates through values and basically adds 1, because every key value pair it gets is an instance of the word, in our example, frog. So if there are 7 frogs found by the mappers, then the value emitted by this reducer will be 7. So when you configure a mapper and a reducer, you just write a Java main, and in here you just say which classes it is that it will be used to do the mappers and the reducers. You specify the input and output formats as a set of classes that you can use or extend here in the MapReduce libraries, and then you just pass it a configuration file and say job client run job. And at this stage, the Hadoop framework will push the map and reduce classes to nodes in your cluster, which are allocated for mapping and reducing, and start the job, monitor the job, and if nodes fail, it will try to restart them by running them on different partitions of the data if they're mappers, and eventually your job will hopefully complete. So maybe that description gives you a clue about the main use of Hadoop. It's really designed for batch processing of very large data sets. Just starting up an Hadoop cluster and pushing the classes around and configuring the mappers and reducers takes a few seconds. And so you're not going to get very low latencies out of a MapReduce job. If you want low latency, say you've got a very large data set that you want to process and you want to be able to do certain queries very, very quickly, what you can do is write a MapReduce job which will generate what we call on this slide materialized views. So essentially you're running a MapReduce job, it's maybe reorganizing its input data set. You get a set of say tweets coming in from many users, and maybe the output of your MapReduce job will be the tweets organized by user. Then you can very quickly go to this materialized view, potentially stored in a database or a NoSQL database, and find the tweets by a particular user because they have already been organized by a MapReduce job, which you can then maybe run in the next hour to create another set of materialized views for the latest set of tweets. So one of the disadvantages of MapReduce and Hadoop is that it prefers reliability over performance. So that means that at every stage in a MapReduce job, things are persisted to disk. And so the mappers will write to disk, the reducers will read from disk, the reducers will write to disk. And this means it has great reliability because if something fails, it can be restarted because the intermediate results have been persisted. But it does lead to slow jobs, especially if you want to write a multi-stage MapReduce job, whereby you take some input, you run MapReduce, generate some output, and then you run another MapReduce job on that output. So Spark emerged from Berkeley and has been an Apache project for the last 3 or 4 years. And it was really designed to get around some of these limitations of MapReduce. The terminology it uses, it's designed for iterative algorithms. So basically, algorithms that will take a data set, process it transform it, process it, transform it, process it again, and eventually produce an output. So the key innovation here is that Spark attempts not to persist everything at every stage in this iterative processing. The key abstraction that Spark uses is a RDD, a resilient distributed data set. You can basically think of this as, but by default it runs on top of HDFS. When you run a job, the partitions that you want to process are read into memory, into the memory of the nodes in the cluster that you're using for processing. Once the data is in memory, it can be transformed and then analyzed by the code that you submit to each worker. But RDDs are essentially immutable. So you load them into memory and then you transform them into potentially other RDDs before you actually do processing on them. So it's a data parallel programming model for fault-tolerant distributed data sets. An obvious point is what happens if an RDD is greater than the size of the memory that's allocated on each node. Well, there's many options in Spark to be able to spill parts of RDDs to disk so that you can process much larger data sets than you have in memory. But Spark's sweet spot is when your data set fits into the memory that you have allocated across your cluster. So here's a very simple example. We have a Spark context which we can then use to create an RDD. So we create a very simple list of integers, and then we create an RDD of type integer, and we say parallelize the list of integers data across 5 nodes. So in this case we're pushing each of the numbers to an individual node, but we've created an RDD that's distributed across 5 nodes. So once you have an RDD, you can transform it. So you can create other RDDs based on that, because RDDs are immutable. So you have to transform them into other RDDs. Once you have the data in the format in an RDD that you want it, you can perform actions on it, which are basically analysis. So if you look at the code on the right here, we take a text file and we create a RDD called line lengths, and we then basically get the length of every line in the RDD. We persist it, so this means that we can come back and process it at a later stage, and then we use a action called reduce, which gets the total line length for all of the lines. So the reduce function produces a result. Actions are executed in a lazy fashion. So when we recreate and transform RDDs, they're not actually processed until we perform an action. Once the action is requested in our code, then Spark will do the necessary creation and transformation of RDD so that we can actually perform our action. And this is designed to enable Spark to schedule multiple jobs on the same cluster more effectively. So, follow these URLs, have a play with Spark, and get a feel for how it works. It's a very powerful and becoming much more pervasive technology for large-scale data analytics.